All right, let's take a look at these first four here. So, I mean, this first one is classic example. You sure as all hell, hopefully you don't want to do that. Write it 6 times, multiply it out. Sounds like fun, but I pass. Thank God that the thing that's stuck, its derivative is out there, off by a constant, but who cares? I can make the constants match. So if I let u equal what? So then du is dx. So of course, what do I need to introduce? 1/15. So then I can put my 15 in there. So this is du, and this becomes u to the 6th. Yeah, sorry. So then I got my 1/15 sitting out there. And then the integral of u to the 6th is 1/7 u7. And then I've got, 7 times 15. 1/5. U to the 7th, u was this guy. Plus c. Thank you. Now, just to get us ready for this, if this would have been a definite interval, right now this is indefinite. There's no defined limits on this thing. But if this would have been a definite interval, it would have told me what x does, because this is all dx. So this is the amount of area I pick up as x goes from whatever to whatever. The minute I go to u, so if x went from like 0 to 1, let's say, I'm just going to add this in just so I can talk about it. What would u do? U would go from, at 0, what's u? 1. So then on here I could say u goes from 1, and at 1, what's u? When x is 1, u is 4. Then I wouldn't even need to go back to my x, because now I know what u does. This is an equivalent integral. I've just transformed it to the u-axis. Right? So these are equivalent integrals. So if I did this and then plugged 4 in and plugged 1 in and took the difference between the two, that would be the answer. Now, to be honest, what I always did when I first took calculus is I never did this. I would always just go, I would do this. I highly recommend you do what I just said, because Jeff was kind of silly. I would do this. I'd say, no, I'm going to remember it's 0 and 1. I put little parentheses because it's not really what u does. It was at what x was doing. Then I would take it all the way back to what x was and bring back the 0 and 1 and put those in. To me, it felt like it was quicker, but to be honest, it's not. You have that one extra step of bringing the x back in. And once you get to Calc 2, Calc 3, and it's all about changing the limits, you really want to be used to changing those limits in this simple way before you get to much more complicated, where the limits involve variable expressions and shit like that. Okay, so I'm going to really push that. If we do u sub on a definite interval like these guys, when you define what u is, that redefines what the limits are. Because those limits started off with what x was doing, now I've got to make them what u is doing. What is you doing? All right. So what about this guy here? Is that going to work with u sub? Yes, because there's a function that's stuck whose derivative is free to move. All right, so this one's not too bad. You're going to let u equal x cubed plus 1. du is 3x squared dx. I just need a 1/3. Yeah, I need a 1/3 out front. So I can put my 3 in there. So now I can read right, this is 1/3 integral 3x squared dx is du. And this is going to be u to the 1/2. Right? Not too bad at all. You gotta love u sub. And then I've got a 1/3. What is the integral of u to the 1/2? Yeah, u to the, yeah, exactly. So there'll be 3/2, and then you multiply by the reciprocal of this. So I get 2/9. U was x cubed plus 1 to 3/2 plus c. Not too bad, right? This is cool. Okay. And then C is another classic problem. So natural log is one where the derivative is 1 over x. So it looks a little different than we're used to. Square roots and those roots are the same idea because when you take the derivative of x to 1/2, you get x to the negative 1/2 with the constant. Who gives a shit about the constant? So this doesn't first look like it's going to work. But if you let u equal, what are you going to let u equal? Square root of x. X to the 1/2, because its derivative is 1/2 x to the negative 1/2, which is what that is, minus a 1/2, right? All right, I like it. So then outside I've got to put a 2, so I can introduce that 1/2 that I need. That's the much better way to look at that than solving for dx. That's insane. So I get twice the integral. All this business here, oops, forgot my little dx there. All that stuff is du. And then here I get cosine u. And of course, integral cosine is sine. I like a positive sign. And let me go ahead and put back in what u is. U was x to the 1/2. So I can write like that again. Yeah. Okay. Now what about D? Let me make some room. Did anybody try D? Did anybody figure out how D works? All right. This is nifty. Once you see this, you got it?
I got as far as breaking up the x cubed.
Good. You got to break the x cubed up. That is one big thing to realize. So, all right. So let me write D over here so I get some more room. So the first really big problem, and some students don't see this as a problem, that u equal x cubed, du is that, somehow that comes out. You know, you're just like trying to force that square peg in the round. Work! It ain't set up to work directly. But if you do don't give up on it. Let u equal x squared plus 1. And then what's du? 2x dx. I do have an x, right? I got 3 of them. But if I do the substitution with what I have, I'm not going to have only u's. I'm going to have some other x thing. In fact, can somebody see exactly how many x's I'm going to have left? Yes, x squared. But don't I have a relationship between x squared and u? So it's substitution. If I can substitute all parts that have x in it with something that has u in it, I can proceed. So there's more flexibility with u sub than you first notice. This means that x squared is u minus 1. So here, let me rewrite this. So I get integral x times x squared, square root of x squared plus 1 dx. X dx, oops, what am I missing for this?
2.
Yeah, I need a 2, so let me do that. 1/2, there's my 2. So 2x dx is du, that's du. Square root of x squared plus 1 is now square root of u, square root, x squared is now u minus 1. Do I have everything related to u now instead of x? Yes. That means everything I did was legal, hopefully. I mean, especially this kind of problems where people do the solve for dx thing and expect magic to happen. They just kind of have an x squared, they push it aside, and then they bring it back in at the end. I'm like, how the shit did that happen? But not sure if you really see what I mean. That's a horrible way to teach it because it makes a student feel like more will work than really will. It's much better to force you to go, do I have what I need? Let me balance what else I need. It's a much better way to look at it. And now what can I do with this? I just distribute now, right? So this will be inside, I get 1/2 integral u to the 3/2, thanks for the help, minus u to the 1/2 du. All right, this is all my u sub work here. And now this is relatively easy. I get 1/2. What happens to this? 5/2, so this will be times 2/5, minus 1/2. That's another thing that people forget. The poor little 1/2 goes on both. This will become u to the 3/2, so then u times 2/3. Ooh, look at that, plus c. C is just waiting for me. So I get 1/5, what was u, x squared plus 1, the 5/2, minus 2/6, bless you, x squared plus 1, to the 3/2 plus c. Oh, shit. Craziness. So u sub won't always work, but it will work more than you first think it will.
I'm sorry, where did the u to the 3/2 come from?
Oh, distribute this.
Oh, okay.
Yeah. All right, all right. Little side note before we do these two. Here's a very related place that u sub works that it doesn't look like it's going to work at first. Let me make some room for myself over here. It's very much related to the one we just did. It's not exactly the same. So if I have something like this, so do you see how this I could do? Because the radical is a single thing. So I can distribute across these guys who are both free. Here I've got 2 terms in the radical and 1 term outside. Do you guys see the problem? If only I could make this to be 1 term and this to be 2 terms, I could do it the same way we just did. So the way I do that is to use u sub where you didn't think it would work. If I let u, now this is going to be a little worse than I thought it, but oh well, too bad. 4x minus 7, what's du? 4 dx, right? And if u is 4x minus 7, that means x is u plus 7/4, right? That's the extra step that a lot of teachers don't even know themselves, I think. So they never even show their students that you could do that. So I can rewrite this now as x is u plus 7/4. Oh yeah, do I have what I need for this guy? No, so how do I get that in there? 1/4, and I can put a 4. Let me go put it where it needs to be. Whoop. So I get 1/4. X is this. Square root of that becomes u to the 1/2. And then 4 dx is the u. So now do you see how I made the radical piece a single term, and the other piece now has 2 terms. So now I can distribute. I can just take that 1/4 out of the way because that's kind of gross, right? So I make this 1/16. Now I can bring the u to the 1/2 through, u to the 3/2 plus 7, u to the 1/2, and that's easy. That's just exactly like what we just did. So when you first look at this, when you first learn u sub, that's not going to work. It's supposed to be a squared there. Then u sub will work. But it's this extra little thing you can do. There's a relationship between u and x. When you're trying to replace all the x stuff with u stuff, bam, use it. I'm not saying u sub does not work for everything. Good Lord, it doesn't. But it works for more than people sometimes realize. All right, let's try this one out. Now hopefully, you've done a few of these now, so hopefully you can see, what am I going to let u be? Ln x. Because it's the thing that's stuck, and what's the derivative of ln x? U, so that's in there, right? So if u is ln x, du is 1 over x dx. Now, extra little piece of side work is this is a definite integral. If I'm changing everything over to u, that means I have to change the limits because they're what x does. They're not what u would do. So what does u do? What does u do? When x is e, u is natural log of that, which is, what's the natural log of e? 1. Because that's the base of natural log, right? When x is e to the 4th, what's u? Natural log of e to the 4th? 4. Because ln and e cancel, leaving with 4. So now I can rewrite this integral as the integral of 1 to 4. Now be really careful. There could be situations where your u sub makes this bigger than that. You don't just switch them because you like the smaller one down. No, no. You gotta, that's got to become that. That's got to become that. No matter what the hell happens. So e to the 4th becomes 4. E becomes 1 for u. 1 over x dx is du. And now I've got 1 over u to the 1/2, which you can write as u to the negative 1/2. Is that cool? U is ln. U to the 1/2 on the bottom. U to the negative 1/2 altogether. All right. And now that integral is relatively easy. And those numbers are going to work really well with the square root. All right. Looks like purple's the only one that's really working good. So what do you get when you integrate u to the negative 1/2?
1/2.
Goes up by 1, so it's 1/2, and then you multiply by the reciprocal. Evaluate it from 1 to 4. You do not have to bring it back to x. You could bring it back to x and then plug these in. But you see how that's kind of dumb? When I did this, I did plug those in already. So now I can just plug these in for you. So this becomes 2 times 4 to the 1/2 minus 2 times 1 to the 1/2. 4 to the 1/2 is 2 times 2 is 4, minus 2 is 2. Yes. All right. What about part B over there? Hopefully this is semi-obvious what to let u be here. You don't want to let u be cosine squared. That would so desperately suck. What's the derivative of cosine squared? 2 cosine sine shit. So you want to let u be what? What kind of determines it sometimes is what's free to move is sine x, really. I mean, right? So if you let u be cosine, then derivative is basically sine, right? So, I mean, constants don't matter. We can make those work. So let's see. If u is cosine, then du is negative sine. That's easy to take care of. Negative, negative. Right? Add a negative out there, so you can put a negative in there. So overall, you didn't change anything. It's the same problem. So then I get, and now you got to think about, okay, if x is pi over 3, what's u? One half. Good. All right. Pi over 3, 60 is far away from x. That's where cosine likes it. It's near where cosine doesn't like it, so it's smaller. 1/2. Right? When you're close to what it likes, it gets bigger. So u is 1/2. When x is 0, u would be 1. So this is a good example of what I was talking about earlier. Negative integral. 0 becomes 1. Pi over 3 becomes 1/2. when I go from x to u. Well, something you guys might realize, you could just make this positive and switch them, right? Because that's, if I switch the order of the limits, I change the sign of the integral, if you want it. And what do I get inside? I get, this is all du, and I get 1 over u squared, so u to the negative 2. Ends up not really mattering that much. I mean, what is the integral of u negative 2? Negative u negative 1, right? So the negatives cancel. You get u negative 1 evaluated from 1 to 1/2. Is that cool? The integral of this is negative u negative 1, so that cancels with that negative. That's why the negatives went away. And now you just throw those in there. So flip 1/2, you get 2. Flip 1, it stays 1, you get 1. Again, that always kind of freaks me out a little bit still when I see that. The integral of that from 0 to pi over 3 is 1. Hey, what the shit? That's nice. I didn't expect that. Is that okay right there? Is that?
Wait, Mark, did you see your cosine?
Maybe. What happened?
Took out, because you have the cosine squared on the bottom, right?
There's a cosine squared. That's why that's u squared.
Oh, okay.
Yeah. U is cosine, so that becomes u squared.
Oh, okay.
Yeah. A lot. Good. Real quick, let me see if you guys were paying attention to something that just happened. Some of you guys are like, I have no idea what just happened. So, what if I had this instead? See, that's a sine 2x. All right, let's see if you guys remember some basic trigonometry. What is the derivative of cosine squared? If I let u be cosine squared, what's du? 2 cosine x. Negative sine x. All right, derivative of cosine, it gets a turn. What is 2 sine x cosine x? Two sine x cosine x is sine 2x. To be really honest, that should be like 7 plus 3 is 10. It really should be. I feel bad for you if that's not true, but 2 sine x cosine x is sine 2x. That's the identity. This comes off of the addition identity for sine, right? So I could do this one. If it was this instead of what I had, I could do this kind of a different way. Because I got exactly what I just need a negative, then that's my du. So this would be negative integral of 1, well, let's see if we can do this. U is cosine squared, so this is just going to be u. So you get 1 over u, so u negative 1, du. Very different, because I had a different thing. I had this guy's derivative in there already. It was, so I could just let u be this whole thing. You guys see that? You know what I mean? So yes, trig identities will show up. And you know I'm going to make it show up on the test when we should. Not to be mean, but maybe a little bit. Not really. But just to try to maintain that in your head. There's got to be some motivation for you to keep that alive because they are incredibly useful. So you should know them. Okay. And then this, just to finish this out, what is the integral of this? Yeah, so this would be ln u plus c, and then you bring back in, I didn't make it definite, so you have to just ln of cosine squared. Okay. a little preview of what's coming, and then I think, let's see, well, maybe a bigger preview of what's coming. I wanted the bulk of today to be devoted to integration, because we had a nice, decent amount of time to get used to differentiation. But then integration was relatively recent, and that's going to rule a lot of everything with however further you go in math. That's going to rule it, just about, is integration. But one of the first things we can start to play with is, so remind me what this does. What does that really do? There's several answers that you can give me here, but a geometrical answer. Finds the area?
Under the curve.
Under the curve f of x from A to B. I like it. So there could be negative area like we talked about. Let's just do that. So this is the total area. Okay, so now let's say that what I really want to do is, let's say this is my f of x here. This is f of x. And what I really want to do is find the area between that function and another function. Now, to be really honest, that's exactly what the shit this is. Because what function is this? What function is the x-axis? What's the equation for the x-axis? You guys can do it. You can do it. What's the equation for a horizontal line? All right, so what's the equation for that horizontal line? Y equals 0. So we already are doing f of x minus 0, the difference between those two functions, because we're just, of course it doesn't show up because it's stupid 0. But let's say I want, here's my g of x. So that's g of x. I really want the area between these two. So what is this? That's too much. How much too much is this? Exactly g of x, the integral of g of x. So to get that area right there, I would have to subtract this much. So what's a slightly better way to write that? I love it. So the area between two functions, it should make sense. Between should kind of lead to subtraction. What's the distance between 7 and 10? No, it's 3. So the area between these two functions is the difference in the areas underneath each that leaves the area between the two of them. Now, there's a lot kind of going on with this. Notice how f is always above g. That's huge. If g was always above f, I better freaking flip those around. The answer to this question can never come out negative. Because there's an area between two functions. If it's negative, what the shit? That doesn't make any sense. Negative area in general makes sense because we know that it means I'm losing stuff and so forth. But the area between two things cannot come out negative. So what we're going to face, really the hard part of a lot of the problems we're going to do related to this will be determining when the functions cross. Which in essence isn't that difficult, but it can lead to interesting equations to solve. So if I have one function f of x, and I say find the area between that function and the g of x function, and well, you got to figure out where the hell do they cross. That could be one first step. I like it. And what really, really sucks is when they cross a few times. Which means if they say from this to this, you have to break this up into two integrals. Because here, f is on top, g is on the bottom. Be like this. Here, g is on the top, f is on the bottom. You better turn them around. So those are the kind of considerations. But even with all that shit, it's relatively simple, thank God. Yes?
Do we ever have to find the area of a piece of it, so the intersects are outside of the A and the B?
Oh, let me think. How do you mean?
Basically just move the A and the B of that one that you have the example.
So here, if this was A and this was B, is this kind of related to what you're asking?
No, on the inside of the board.
Because I don't know what this is doing outside of A and B, right? So is it, what if it was doing this, right? And this is going this, right? 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 I mean, is that?
I'm saying if you move the A and the B, like.
Oh, I see. Yeah, totally. Some of them are going to tell you from here to here.
Yeah, yeah.
So it doesn't matter where they cross. You just have to worry, do they cross each other within that interval? Or they're going to say, find the area between these two, enclosed by these two, they might say. And then you got to find where they meet. That's going to be your interval that you integrate across. So those are the two main types of problems you'll see in the section. I like it. I like it. This, by the way, the section I'm talking about is section 6.1. We just did 5.5. That's U sub. I like it. 6.1 is finding areas between functions. 6.5 is finding the average value of a function. Those are two relatively simple things. 6.2 and 6.3 are interesting. To me, I love it. I have the most colorful handouts I've ever made for those sections. When I first took it, I didn't understand it worth shit, just to be honest. I remember this very well, and it was just all because of the way it was shown. It just didn't make any sense. It was all very technical, and I didn't see any connection to something. So have you ever seen the, for me, it was the Thanksgiving decoration that my parents had. It was a turkey thing, and when you unfolded it, would open like an accordion, and it would have this. I actually have one. A student of mine a few years ago gave it to me because they kept talking about it, and they found an example. I'm like, oh, sweet. Since I moved, I moved offices. I have no idea where the hell it went to. But has anybody ever experienced this? You open it up, and it just unfolds like an accordion thing. So it could look like this, and when you open it, it becomes a full sphere. So what we're getting into with 6.2 and 6.3 will be, here's a function, what's the volume if you rotate that around the y-axis or the x-axis for that case? That sounds horrendous. The beautiful thing is, the two main approaches we take are based completely in easy-ass geometry. Sure, Jeff, whatever you say. But what's really nice is we then make some better connections between the shape of something and its volume formula. We can actually derive it using calculus, which is beautiful. We just have to figure out, how do I do this rotation thing? How does that come into play? There's two main ways to do it, and the hardest part for students is, when do I do which way? And that's that handout that's really colorful, trying to explain to you when to tell which way to use. That's, to me, is the hardest part. Is, when do I use which way? Is there a better time? Yes, there are very specific things you can look for about which way to do. All right, so that's a little overview of what's to come. So tomorrow we're going to start with a quiz. We're going to do as much as we can in Chapter 6. I'm probably going to do 6.1 and 6.5 first, because those should be quick. And then I'll do as much as I can in the other ones. And then whatever's going to be on the, whatever you have to finish will be, we finished on Monday, and then we have the review for the test on next Tuesday. Cool. So we have a quiz tomorrow, 4953. Be ready for that. Right. Otherwise, I think that's plenty for today. I'll let you guys out early if you guys look fried. Thank you.